Let's explore what it means for a conductor to be in electrostatic equilibrium. Let's look at a conductor, a solid conductor. And let's focus our attention on two charges in this conductor. We'll look at two negative charges. Let's take a look at a conductor. And let's look at two negative charges in this conductor. Now, you know that surrounding every charge in space is an electric field. That electric field communicates electric forces with other charges. So in this case, the electric field of these two negative charges will establish electric force of repulsion between them, forcing the charges to move apart. For these point charges, due to Coulomb's law, these point charges will repel, and they will continue to push each other apart until they arrive at the surface. So one charge is here, one charge is there, and they have the electric force of repulsion between them. These charges accelerated to the surface of this conductor due to the electric repulsion between them. Now notice, once it gets to the surface, there's a component of these electric forces that will push them along the surface. So let's take a look. If we look at this charge on the top and look at a line that is normal to the surface, notice that line normal to the surface means that there are two components of the electric force on this charge relative to the surface. There is a component that will continue to try to push the charge away from the surface, trying to pop the charge off the surface. I'll just call this F perpendicular, for perpendicular to the surface. Now I guess I should label this force F, and there is a component that's tangent to the surface that is going to try and cause the charge to move along the surface. And I'll call this portion, let's call it Ft, for the force that is tangent to that surface. Now the same is true for this other electric charge. This other electric charge, if we draw a line that is normal to the surface, there is a component of this force that is perpendicular to the surface. We will call this component, again, F perpendicular, but it's for this different charge. The perpendicular component on this charge might be different than the perpendicular component on the other charge. So I'll label that as F perpendicular prime. And there is a component of the force that is tangent to the surface. So I'll label this as Ft prime. Now, if the binding force of the charge to this conductor is strong enough, then the charge will be constrained to stay on the surface. It's not going to pop off unless the force of repulsion is strong enough to cause them to escape the binding force that it has with the conductor. But what will happen is these two charges will accelerate along the surface until they reach a point of electrostatic equilibrium. So for the top charge will accelerate counterclockwise on that surface. And let's say that top charge ends up right here. And the charge on the bottom will also accelerate until it reaches electrostatic equilibrium. And let's say that occurs right here. Now, these two charges are still exerting electrical forces of repulsion on each other. But notice, they arrive at a point in which the only component of the force that is acting on each of them is perpendicular to the surface. At this point, these two charges are in electrostatic equilibrium. So what is electrostatic equilibrium? Electrostatic equilibrium is the state in which each charge is stationary and has zero net force acting on it. So let's look at what happened here. In the first diagram, the charges were freely wandering within the conductor. However, well, let me rephrase that. In the first diagram, we had positioned these charges in the conductor, but because electrons are free to move in a conductor, these two charges exerted electric force of repulsion on each other, forcing them to move to the outside of the conductor in diagram 2. So moving to the outside of the conductor in diagram 2, there was a component of the force on each of them that was perpendicular to the surface, trying to push them off the surface. And there's a component of the force on each of them that's tangent to the surface. That tangential component of the force caused those charges to move along the surface until finally there's only a component of the force perpendicular to the surface. At that point, these two charges are in electrostatic equilibrium. They're not moving anymore, and the net force on them is zero. And you might be thinking, well, Mel, in the picture, there is a net force on each charge. Well, actually not. What I haven't been drawing is the binding force that the surface has with each of these charges. So I've mentioned the binding force, but I didn't draw it in my picture. Like in this example, in diagram 2, the binding force will take it to be perpendicular to the surface. And in this diagram, which I'll label as diagram 3, the binding force is perpendicular to the surface on this. And so we are in electrostatic equilibrium. So notice what happened with these two charges. These two charges moved to the surface. So we can say that for a conductor in electrostatic equilibrium, excess charge, so we could say any net charge or any excess charge resides only on the surface. If we had multiple charges, I'll just illustrate 3 charges here. Let's say we have 3 negative charges distributed within the volume of this conductor. Now, right now, these charges are free to move, and they're exerting electrical forces on each other. There's an electric force of repulsion between these two charges. There's an electric force of repulsion between these two charges. And there's an electric force of repulsion between these two charges. These electrical forces will cause the charges to move to the surface. These charges will move to the surface until electrostatic equilibrium is established. When electrostatic equilibrium is established, the net force on each of these charges will be equal to 0. The perpendicular component of the electrostatic force on each of these charges will be offset by the binding force the charge has with the surface. And these charges will distribute themselves around the surface in such a way that the tangential component of their force goes to 0. So these charges will redistribute until they reach electrostatic equilibrium. Let's write that down. Charges will redistribute on the surface of a conductor until electrostatic equilibrium is reached.